This is Mr. Potter. In our last video, we talked about how we could come up with a geometric series to represent a whole slew of different functions, from rational functions. We were able to produce a logarithmic function. We were also able to produce a trigonometric function. And, you know, it would really be nice if we could come up with some type of polynomial approximation for virtually any function. And that's what we're going to be talking about today. So I want to talk about how we would exactly go about building a power series. So let's say that I want to figure out something about the natural log of x. Now, the problem I'm going to run into is that I can't really take the natural log of 0. So I'm going to want to substitute some other number that's easy to take the natural log of, like 1. But in order for this to work out, I'm going to want some of my terms to disappear. So I'm going to write this as a times x minus 1 plus b times x minus 1 squared plus c times x minus 1 cubed plus d times x minus 1 to the 4th. And I should be able to continue this out forever. I'm hoping that in looking at these different patterns of A and B and C and D, that I'm going to find some type of pattern that will allow me to make predictions about what the terms of this series should end up being. So I know that the natural log of 1 is 0. And looking at this, that gives me a times 1 minus 1 plus b times 1 minus 1 squared plus c times 1 minus 1 cubed plus and so forth. All of these terms are going to go away. But if I take a look at the derivative, I know the derivative of natural log of x is 1 over x. And if I take a look at the derivative evaluated at 1, that should be equal to the derivative of this evaluated at 1. Well, the derivative of this function would be a plus 2b times x minus 1 plus 3c times x minus 1 squared plus 4d times x minus 1 cubed and so forth. But if I'm substituting x equals 1, each of these terms should go away, leaving me with just a. And so I find out that a must be 1. If I want to look at the second derivative, the derivative of 1 over x, is negative 1 over x squared. So if I try to evaluate the second derivative at 1, I'm going to get negative 1 over x squared, which is really be just negative 1 over 1. But if I'm looking at the second derivative of this polynomial, this actually ends up being 2b plus 6c times x minus 1 plus 12d times x minus 1 squared plus, and so forth. And if x is equal to 1, all of these terms should go away, leaving me with just 2b. So I know that 2b equals negative 1, and so b has to be negative 1 half. And if I continue this idea, taking the derivative of my functions, now I'm at the third derivative, which is 2 over x cubed. And if I try and evaluate f triple prime at 1, which should be 2 over 1 cubed, which is 2, that has to be equal to the third derivative of this power series. So the derivative of a constant is 0. The derivative of this term would be 6c. The derivative of this term would be 24d times x minus 1 plus, and so forth. But substituting in x equals 1 makes this term disappear as well. So I've got that 6c has to be equal to 24, and so, excuse me, that 6c has to be equal to 2, and so c ends up being a positive 1/3. And if I try this one last time, if I take the derivative over 2 over x cubed, I'm going to get negative 6 over x to the 4th. And if I try and evaluate this fourth derivative at 1, I'm going to get negative 6 over 1 to the 4th, which is negative 6. But now if I take a look at this derivative here, this has got to be equal to 24d plus, and each of these other terms, which I haven't bothered writing, are still going to have those x minus 1 terms. X minus 1 to the first in the case of this one, because I've taken 4 derivatives. This next term over here that was hidden was really e times x minus 1 to the 5th, and so this is going to end up being 120 e to the times x minus 1. So, but all of these terms are going to end up being 0 because 1 is equal to x. So what I've got is negative 6 equals 24d so d equals negative 1/4. So my power series should be equal to natural log of x equals a times x minus 1 plus b times x minus 1 squared. Well, that's negative 1/2 x minus 1 squared plus c times x minus 1 cubed, so that's 1/3 x minus 1 cubed plus d times x minus 1 to the fourth, so that'd be negative 1/4 x minus 1 to the fourth. And I can see that there's a pattern here. I see that my denominator of these fractions needs to be equal to the exponent of the x minus 1 term. I notice that I have an alternating series because I start off with a positive coefficient, then a negative coefficient, then a positive coefficient, then a negative coefficient. And what I've really got here should look familiar to what we were talking about in our last lesson, that the natural log of x equals x minus 1 plus x minus 1 squared over 2 minus plus x minus 1 cubed over 3 minus x minus 1 to the fourth over 4 plus. So in other words, just looking at the values of successive derivatives and comparing them to what they should be in a polynomial actually gets me a series that looks very similar to the geometric series that we were talking about. Now, I did this with natural log. I'm interested in seeing what happens if I try and do it with a different function. Let's say I want a power series for e to the x. So I'm going to start off saying that e to the x is equal to a plus bx plus cx squared plus dx cubed plus ex to the fourth plus and so forth. And I'm hoping after I get enough terms, I'll be able to find some type of pattern. So I know that e to the 0 power is 1. But if I substitute 0 into this polynomial, this is going to be a plus nothing plus nothing plus nothing plus and so forth. And so I find out that a must be equal to 1. And the derivative of e to the x is e to the x, which is going to be very, very convenient. So if I'm trying to find the first derivative at x equals 0, I'm going to e to the 0, which is 1. But taking the derivative of this term means this is a constant that goes away. This ends up being b plus 2c x plus 3d x squared plus 4e x cubed, and so forth. But each of these terms here are 0. And so I'm just going to have that b equals 1. And if I take a look at the second derivative at 0, that's also e to the 0, which is 1. But taking a look at the second derivative here, I'm really taking the derivative of these terms. That's a constant, so it goes away. This is 2c plus 6dx plus 12ex squared. And so I end up with 2c equals 1, or c equals 1/2. And if I continue this after triple prime of 0, that's still e to the 0, which is 1. But this ends up being 6d plus 24ex plus, and so forth. So if 6d equals 1, then d equals 1/6. I'm going to do one more step. This is my fourth derivative at 0, which is e to the 0, or 1. But this is really equal to 24e plus polynomial terms in x. So e ends up being 1/24. And so what I end up with is a power series for the e to the x function. E to the x ends up being 1 plus x plus x squared over 2 plus x cubed over 3, 6, excuse me, 6, plus x to the 4th over 24, plus, and so forth. And the thing is, keep in mind, the reason that this is 24 is this is really 4 times 3 times 2 times 1, or what we would call 4 factorial. Similarly, this is 3 factorial. And this is a rather boring way of saying 2 factorial. And I could have called this 1 factorial. And what we remember from our pre-calc class is that 0 factorial is equal to 1. So this is really over 0 factorial. So my generic term would be x to the n over n factorial. And in fact, what we have as our power series for e to the x is that e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial. Now, what's really nice about this, and something we'll talk about in class, is in our geometric series, we were bounded by this interval of convergence, where the interval of convergence had to be between -1 and 1. But this is actually true for all values of x. In other words, my interval of convergence really goes from negative infinity to infinity. And we'll talk about why that's true when we talk in section 9.3. But this power series really does have a lot of power behind it. The idea that we can write this exponential function, this function that involves a transcendental number, as polynomial terms, and we can get whatever degree of accuracy we want by just adding more terms to the sequence. Now, I've done this with e to the x, but I can also do this with some other functions. So let's talk about what a power series for sine of x would look like. So looking at this, I'm going to say that sine of x is equal to a plus bx plus cx squared plus dx cubed plus ex to the fourth plus fx to the fifth plus gx to the sixth. And I'm only doing this to show a point. Hx to the seventh. And of course, technically, this is an infinite power series, so it does go on forever. The powers go to n without bound. But I'm going to be looking at my function evaluated at 0, which is the sine of 0, which is 0. And in order for this polynomial to be equal to 0, a must also be 0. But when I'm looking at f prime of 0, the derivative of sine is cosine of 0, which is 1. And when I take the derivative here, this is going to be b plus 2cx plus 3dx cubed plus 4ex 3dx squared plus 4e to the x cubed plus 5 fx to the fourth plus 6 gx to the fifth plus 7 hx to the sixth plus ... And so I find out that in order for this to be equal to 1, that b must be equal to 1. The second derivative at 0 is negative sine x, but negative sine of 0 0. And so that means all of these terms must be 0, so c must be 0. Because that's the only term when I take the second derivative that doesn't involve x. If I take the third derivative at 0, that's negative cosine of 0, which is negative 1. But taking a look at the derivatives here, I'm going to end up with six d plus 24 e x plus, that's going to be 5 times 4 times 3. So 5 times 4 is 23. So that would be 60 f x squared plus, this is going to be 6 times 5 times 4, or 120 g x cubed plus 7 times 6 times 5, that's going to be 350 h x to the 4th. And so in order for this to work out, 6d has to be equal to negative 1, and so d must be equal to negative 1/6. And when I look at the fourth derivative at 0, I'm back to sine. And so what's going to happen is that all of these even terms are going to involve sine, and so that means that all of my even powers actually end up going away. Now, we know that sine is an odd function, and we know that if we take odd functions and add them to odd functions, we end up with an odd function. If we take an odd function and add it up to an even function, we actually end up with the neither function. So it makes sense that I should only have odd terms left over. So I need to know what's happening for the fifth derivative at 0, which brings us back to cosine of 0, which is 1. But I'm looking for the first derivative, the fifth derivative. That's gone, that's gone, that's gone, that's gone, that's gone. And if I've taken the derivative 5 times, this is 5 times 4 times 3 times 2 times 1. So this is really 5 factorial times f. And so f really ends up being 1 over 5 factorial. And if I continue this, I'll find out that h ends up being negative 1 over 7 factorial. And I end up with a power series for sine x that involves only the odd terms. So the sine of x ends up being equal to the first odd term, which is 1x. And then the second odd term is negative 1/6. That's really minus x cubed over 3 factorial. The next term is the fifth power, which is positive, so that would be x to the fifth over 5 factorial. The next term is negative, and it involves the seventh degree, so x to the seventh over 7 factorial, and so forth. So I could really say that sine of x has to be the sum from n equals 0 to infinity of odd powers over odd factorial. So x to the 2n plus 1 power over 2n plus 1 factorial. But the only thing I haven't taken care of is the fact that this sign alternates. And the way I can do that is by taking negative 1 to the n. So if n is even, like here n is 0, here n is 1, here n is 2. For my even n's, the terms are positive, and for my odd n's, the terms are negative. And so this is the power series for sine. I can do the exact same thing for cosine. So looking at it for cosine, I find out that cosine of x, if cosine is even, then I really only need to take a look at the even polynomial terms, which would be a plus bx squared plus c x to the fourth plus dx to the sixth, and this is going to go on forever for even terms. All of my odd terms should go away. So when I'm looking at f of 0, that's cosine of 0, which is 1, and so a must be 1. If I'm looking at the second derivative of 0, that's negative cosine of 0, which is negative 1. And so I end up with c being equal to, with b being equal to negative 1/2. Now, this is really 1 over 2 factorial that I'm dealing with, because it's really 2 times 1, and we'll see that as I go through more examples. The fourth derivative at 0 ends up being back to cosine of 0, which is a positive 1. And so c ends up being 1 over 4 factorial, because I'm going to take this derivative 4 times. I get 4 times 3 times 2 times 1. And similarly, the sixth derivative at 0 is cosine of 0 negative, which is negative 1. And so d ends up being negative 1 over 6 factorial. And so we end up with a Taylor series for cosine of x, because here I'm adding up from n equals 0 to infinity the even powers, and this is over the even factorials. But I still run into the idea that A and C are positive, but B and D are negative. So I still have this alternating sign, so I'm still going to have this negative 1 to the n. And in fact, these three series that we've talked about for sine, cosine, and e to the x, these are really good series to memorize for the AP exam, because we do see lots of combinations involving sine, cosine, and e to the x using these power series. Now, these power series have a name, and they're named after the mathematician that discovered them, who was Taylor. And so what Taylor's theorem says is that if I'm dealing with a function f of x near x equals a, I can say that f of x is equal to the sum from n equals 0 to infinity of the nth derivative at a times x minus a to the n over n factorial. Now, we've seen this n factorial show up in all of our terms. We've seen this nth derivative of a show up a lot with our sine and with our cosine. The idea that this sign, the negative one and the positive one, alternated. And we've been dealing with at x equals 0 or at x equals 1 in the case of our natural log. So we can see how this is a shift going on. And what this means is that if I want to come up with the Taylor theorem for any function, I can do this as long as I can take enough derivatives to see what's going on. So I can actually come up with the fourth degree Taylor polynomial for tangent. So I could figure out at x equals 0. So I know that f of 0 is really the tangent of 0, which is 0. F prime of 0 is secant squared of 0, which is 1. I can do f double prime of 0, which means I'm taking the derivative of secant squared, which would be 2 secant to the first x times the derivative of secant, which would be secant x tan x. But substituting in 0, I find out that I actually do end up with 0. The third degree of this, I'm going to have to treat this like a product rule, because I've got 2 secant squared x times tangent x. So this is really going to be first times derivative of the second plus the second times the derivative of the first, which is going to be 2 secant x secant x tan x times tan x, with a 4 here instead of a 2. But when I substitute x equals 0, I get 2. And I've tried to do the 4th degree polynomial, and I end up with 0 because I know that the tangent is odd. So I shouldn't have any even polynomials. And so my 4th degree Taylor polynomial is going to be, well, I have no constant term, I have no quadratic term, I have no quartic term, I just have a linear and a cubic term. So this should be 1x to the first over 1 factorial plus 2x to the third over 3 factorial. And so what I see here is I see x plus x cubed over 3, and I can continue this. I'll find out that I end up with x to the 5th over 5, x to the 7th over 7th, if I wanted to continue this Taylor polynomial for tangent. Now, I can do this for any function, provided that I know how to take an arbitrary number of derivatives. If I'm doing a 4th degree polynomial, I need to know how to find the 4th derivative of a function. But we've been taking derivatives all year. I need to be able to substitute a particular value of a. And ideally, I'm looking for a value of a that's relatively simple to substitute. And we have this notion of in factorial, the idea of taking a number and multiplying it times its predecessor all the way down to 1. Now this was Taylor's theorem, and Taylor's theorem is helpful because it allows us to do any particular a value. So I can do any translation to the left or to the right. There's a more specialized version of this theorem called MacLaurin's theorem, which deals exclusively at 0. So if I want to find f of x near x equals 0, then what happens is f of x ends up being equal to the sum from n equals 0 to infinity of the nth derivative at 0 times x minus 0, so that's really just x to the n over n factorial. And the thing is, we'll actually use MacLaurin's theorem a little bit more than we'll use Taylor's theorem, simply because it's often very easy to substitute x equals 0 into polynomials and get very, very standard values from them. So we're going to continue talking about applications of Taylor's theorem and MacLaurin's theorem throughout this class. We're going to be talking about how do I find the accuracy of these approximations, because I certainly can't type in an infinite number of polynomial terms. How many terms do I need to get accuracy to the hundredths place, or accuracy to the thousands place? We'll talk about all those in future lessons, though. This is Mr. Potter. Thank you for watching. Have a great day.